So let's get started with our first topic, which is measuring the Earth, seeing how big the actual planet is that is around us. So if we look at the Earth on the screen, you'll see a couple of interesting numbers and details. Here we have the average diameter of the Earth. Once again, that's giving us an indication of roughly the shape that we're going to be talking about. We're talking about diameter. We're obviously talking about a circular object. And we're talking about the distance across that circular object. And we have the number here of roughly 12,735 kilometers. Now, if you're looking at all the measurements quick on this chart, you'll notice that they're all in the metric system. Why is that? Because that's the system that we're going to use in this class. We're going to strictly use the metric system. We are not going to use the traditional American system because that is the system that is used around the world. If anybody's watching this anywhere else in the world, that should make sense to you. But to my American viewers, it can get a little tricky. We look at the circumference. Here we have the circumference. This is going to be the average circumference around the equator. Remember that term that I used, average and equator. It's going to be important in a minute. Of about 40,009 kilometers. The density, you've done density innumerable times at this point as a student, of 5.51 grams per milliliter, making the Earth obviously much denser than water, but we have to remember that this is also an average density. If we look at the Earth as we work our way through it, we will find that that density does change. And finally, we have the mass of the Earth right about 6 times 10 to the 24th kilograms, specifically 5.98 kilograms, times 10 to the 24th kilograms, I should say. And that makes us a chunky little monkey there, doesn't it? Now, if we look at the shape of the Earth here, okay, when we're talking about the shape of the Earth, okay, originally scientists, or not so much scientists, but people in general would have thought that the Earth looked like this. Here we have the classic flat Earth. Amazingly, this is a model that's made it back. We'll get to that. But this is the view that many in the ancient world, and unfortunately a few in the modern world, held, that the Earth was a flat disk. And it's actually not a strange view to have, because if you look at a lot of the things and you trust just your immediate observations and you don't go into depth, then it does appear that we are on an unmoving plane and that everything in the universe is going around with us. But if we're good scientists and we pay attention to the details, we notice that there were certain things that were a little bit off, certain aspects that wouldn't quite fit this narrative that was being played. And those questioning minds are the ones that helped us to develop the proper shape of the Earth. Okay? But what do we talk about? You hear a lot of people going, oh, the Earth is flat. Look, if I look, I can see it's flat. It looks flat in front of me. Well, here's an image that I found that's a wonderful image. If you take that camera that you see in the picture and you put it right up against the basketball and you look through the viewfinder of that camera, this is the view you will see of the basketball. If you were a tiny enough creature that could exist on that surface of the basketball, you would say, of course the basketball is flat. Look, it's so obvious to me. The basketball is flat. But when we go out and we see the wider range, we can see that that is most certainly not true. Okay? But it's a matter of perspective. And so we have an issue with our own eyes and our own perspective. And we have to realize that we have to take a step back to truly understand what it is that we're looking at. Once again, here's a funny example from modern culture, the infamous canyon run against the Death Star in the Star Wars movie. If you were doing it like this to a person in an X-Wing or the Millennium Falcon in Episode 6, oh my God, it looks like it's flat. It's perfectly flat. But we all know it's not. But once again, it's a matter of scope, size, and perspective. Okay, here's an image taken from the top of the tallest mountain in the world, Mount Everest, and you can clearly see the curve above the person in the picture. Now, we have to say that this was taken with a camera that had a slightly curved fisheye lens, so it's going to cause a little bit more distortion, but I thought it was a really good image to show. So, if we're looking at it, what is the true shape of our planet? Because normally we'd say, yes, it's obviously a ball, but it's actually not. The Earth isn't a perfect sphere. The Earth is actually what we call an oblate spheroid. What does that mean? It means, much like a lot of us at my age and maybe some of your older aunts or uncles or people, it's a little bit thicker around the middle than it should be. Okay? The Earth is kind of a flattened sphere. At the equator, it bulges a little bit. So it's actually a little bit wider at the equator than it is circumpolar. It's a strange shape. it's very hard to notice. It's a very small, tiny little difference. If you look at the image on the screen right now, you'll see the diameter from, if you went from pole, from the equator across, is roughly 12,756 kilometers, whereas the pole diameter, the diameter from the North Pole to the South Pole, is 12,714 kilometers. So there's a discrepancy there. There's a difference there. Okay, it's not huge. And when we look at images of the Earth, it's very difficult to see. The images that you're seeing are a little bit exaggerated to show it a little bit more, but you're talking a difference of 56 minus 14, so that's 2. That is 42 kilometers. That's not a huge difference on the scale of the planet that we're talking about. Now, that's the Earth if we look at it with all the water and the atmosphere and everything. If we just look at the solid portion of the Earth looks like a weird sort of lumpy potato, I guess would be the best way to explain it. Here's an image that you see of what the Earth looks like, just the solid portion of it. There are portions of it where it bulges out. You notice one over towards the Pacific, and there are areas like right underneath the subcontinent of India and certain other areas where it actually dips in. So the actual solid shape of the Earth is this kind of weird potato-ish shape. But typically the shape that we're going to be looking for if we're being asked on a test or a quiz is that we are looking at a object that is an oblate spheroid. That is the shape that we want to be going with if we're talking about the actual shape of the Earth. Okay, so if we're looking at the Earth, we typically divide the Earth up into what we call the spheres of the Earth. We kind of stick with that spherical shape, and so we divide the Earth into these different spheres that we want to talk about. Okay, different aspects that make up the whole planet. Okay, so when we look at the spheres, okay, we have the different portions. You can see chunks of them here. You have the solid portion. Here you have the liquid portion sitting there on top. We would have the atmosphere above that, and then we have the living, what we would call biosphere, that engages all three portions. Okay, if we look at this image here, we have the picture of the Earth. The little blue bubble that you see there would be all of the water if it was compressed into one tiny little sphere itself compared to the solid portion of the Earth. And the image you see on the other side, the little pink bubble, would be all the gases that form the atmosphere collected into a sphere as well. So to show you that the bulk of our planet is primarily, mostly made up of this solid portion that we are talking about. So the first sphere we're going to talk about is the hydrosphere. The hydrosphere would be the watery portion of the Earth. The portion that's made up primarily of H2O, the molecule that makes up water, the molecule that is water. Okay? If we look at it here, we have a beautiful sunset or sunrise over the ocean, and obviously the ocean would have huge amounts of the hydrosphere. It would make up a huge portion of it. It does not make up the only portion of it, though. We have a solid portion of the hydrosphere, which is the water that is locked inside the glaciers that exist primarily at the poles, or the ones that exist on the tops of mountains or areas of higher elevation that exist across the planet. Obviously, we have issues with these melting and all sorts of things going on now, but we'll talk about that later when we get to our climate change section. Okay, we also have the freshwater portion of the hydrosphere. This would be the streams and the rivers. Okay, and then we have the portion of the hydrosphere that is locked in underneath the Earth, what we typically refer to as groundwater. And when it comes out, we have springs. Okay, some of you may be drinking spring water right now. I'm not going to say the name because I don't have the right to use any of them, but some of you may be drinking water that came from a spring. They are very popular, and there's a large portion of our water that is locked in just below the surface in things we call aquifers, and we'll talk about those when we get to groundwater. Okay, so if we look at the actual hydrosphere itself, what we'll see is that most of our hydrosphere is made up of salt water. You see it's at 97.5%. Only a small, tiny, little sliver of that is the freshwater. Okay, if we look at the zoomed in portion right there, we will see that of this, a huge percentage of it is actually locked inside of glaciers. Okay, over almost 70% of it is locked in glaciers, and 30% of it exists as groundwater, and only 0.3% of it is flowing water, what we would consider lakes and rivers. This, ladies, gentlemen, and everybody else, is the reason why it is so crucial that we maintain our fresh water supply and that we help everyone in the world have access to water, because the amount that we actually have access to that we can use without desalination, which is an expensive and timely procedure and a costly procedure, is incredibly small. So we have to take care of what water we have, which is why water pollution and access to water is an incredibly huge issue that has been both environmentally important and politically important for a very, very long time. Throughout the history of man, countless wars have been fought over access to water, water rights, and things like that. So it is critically important that we protect this fresh water portion of our hydrosphere. The next sphere that we're going to talk about is the atmosphere. The atmosphere is the gaseous envelope that encircles our planet. It's a mixture of various volatiles, gases that exist on our planet. Okay, it forms an incredibly thin little envelope. This is a beautiful picture. I love this image. Okay, there you have the dark curve that would be the surface of the Earth. That pinkish layer is the top of the troposphere. Sorry, and that would be the area where all the weather happens, where you find living things, animals for the most part. And then the layers going all the way up, would be the building and building layers of the atmosphere, getting thinner and thinner and thinner until we reach the very beginning of space. This is just a beautiful image, and it's a moving image to me. I hope you find it interesting as well. Once again, any images that you see, you want to screenshot, just pause the video. Feel free to take the screenshots and use them in your notes however you see fit. Okay, here we have a map, thanks to the great state of New York, of the selected properties of Earth's atmosphere. Okay, we have the altitude. Now this is good because it gives you the altitude in both miles and kilometers for those Americans and non-Americans that might be watching this. So you get used to it. Here we have the different layers. We have the bottommost layer of the troposphere. Then we have the stratosphere and the mesosphere and then the thermosphere. You notice the dashed lines, those represent the boundaries between the layers. We call them pauses. Okay, and they're given the name of the layer that comes before them. So tropopause between the troposphere and stratosphere, stratopause between the stratosphere and mesosphere, and mesopause between the mesosphere and thermosphere. Here we also have a temperature graph for the different layers. You see how the temperature does change. It's not necessarily what you'd expect, but we'll talk about why that happens. There we have the pressure. You see most of the pressure tends to be down towards the bottom. Why? Because you have the most amount of weight pressing down on the surface, so your atmospheric pressure is the highest. And then you have the percentage of or concentration of water vapor in the atmosphere, and you see most of the water vapor is located in the troposphere, which is why we have the weather patterns there. When we look at the atmosphere, we have to acknowledge that the atmosphere isn't purely made of one particular gas. Now, if I was to ask you what gas you think the atmosphere is made of, most of you would probably say oxygen. Maybe some of you would say carbon dioxide because you've heard a lot about it with global warming and stuff like that. Both of you would be wrong. The actual major contingent of our atmosphere is nitrogen. There are a variety of reasons why we think this is. We will talk about that when we talk about the formation of our planet and its development over many, many eons. Okay, but the primary gas, like we see on here, is nitrogen at about 78%. Oxygen makes up about 21%. And then we have a mixture of other gases like argon, which is 0.93, carbon dioxide, which is a very small percentage, which is one of the reasons why we worry that if we increase that, it might have problems. We'll talk about that later. And then we have what we call the trace gases, which would be like your neons, your heliums, methane, water vapor, amazingly very small one. You'd think that would be higher, but it's not. And various other gases like ozone and xenon and things like that. The next sphere we're going to talk about is the biosphere. The biosphere is the portion of the Earth that is living, the organic portion. This would be all the animals, the plants, the corals, the fish. Okay, anything that we would consider to be organic or living makes this up, and it interacts with all aspects of it and affects all aspects. Now, all the spheres do have effects on each other, but the biosphere would be the part that we are members of. Okay, you spent the whole year learning about this in biology. So I'm not going to spend a lot of time talking about that, but this would be the portion that is primarily focused with that field of study. The geosphere would be the last sphere we're going to talk about, and the geosphere is the solid, the tough, the portion that you've seen in the background of this slideshow. This would be the rocks, the soil, the dirt, the stones, the volcanoes, the earthquakes. This is the stuff that we typically think of when you're going to sign up for a geology course. If we look at the geosphere also has a makeup. Okay, here we have a percentage of the different elements that we find in the crust, which would be the outermost portion of the geosphere. Okay, most of the crust is made up of silicon and oxygen. They combine to make a molecule that we call silica. Get used to that one. Then we have aluminum and iron and calcium, potassium, sodium, magnesium, and hydrogen, and then other trace elements. Okay, this is a very wide myriad of elements that we have, but you notice it's not as wide when you look at the entire periodic table. A specific grouping of them that we tend to find in our crust. These are the minerals that or the elements, I should say, that tend to make up most of the minerals, which we deal with in an everyday sort of event. If we look, the geosphere is further broken down into multiple layers. Okay, we have up here the crust, which is this thin little layer. And the crust is actually broken up into two different types of crust, generically. We have our oceanic crust and our crustal crust. One of them is granitic or felsic. The other one is mafic or basaltic. Okay, if you look at the numbers here, you have the densities for the two of them. The density of the oceanic crust is a little bit higher. It's about 3 grams per cubic milliliter, whereas the density of the continental crust is about 2.72 grams per milliliter or cubic centimeter. And this is going to lead to all sorts of issues that we will eventually discover will be the causes of things like plate tectonics or continental drift. Well, not necessarily the causes, but one of the indicating factors. We then have the mantle, which makes up the large portion of the inside of the Earth. Then we have the outer core and the inner core. We will deal with these charts when we talk about the Earth's interior, but once again, you can see that there are variations in pressure, variations in temperature as our depth gets higher and higher and higher. When we look at the inside of the Earth's internal structure, here we go. Once again, we have our lovely image. Okay, we have the crust, which the basic example that everybody likes to use is an apple. So think of the crust like the skin of the apple. You have the meat of the apple, which would be the mantle. Okay, and it is partially molten, which we call plastic. That allows it to flow and bend, but it's still solid. But it's a unique state that occurs when you put something under extreme amounts of heat and pressure. We'll talk about plasticity as the year goes on. And then we have the core broken up into an inner core and an outer core. The outer core being liquid, once again, like we said, the inner core being solid. As the Earth spins, this helps to generate our magnetic field, which is incredibly important to life. Once again, here we have the three spheres that we talked about, hydrosphere, troposphere, and the crust portion of the geosphere. And we have the average chemical composition. For the crust, we have both percentage by mass and percentage by volume. Notice that they are slightly different. Okay, and in the hydrosphere, notice we have a lot less materials, and the troposphere as well. We have a lot less materials making them up. Now, all these spheres that we have interact with each other. They are not isolated from one another. There is interaction between them, and that interaction leads to all the dynamics and all the things that we have going on the planet Earth. Okay? The Earth is what we would refer to as an open system, not a closed system. It's referred to as an open system because we constantly have the input of energy coming from the sun. The sun is constantly bathing us in radiation, and that radiation leads to all sorts of events happening. Also, the Earth has the energy from within itself, from its leftover heat from its original formation, as well as the heat released by minerals that are decaying naturally radioactive decay. It's not a closed system because, like I said, we constantly have this influx of energy from space. If we were a closed system, we would only have a certain amount of energy, and that would create all sorts of problems that we have. being an open system allows us to change and develop, and is the driving force behind things like evolution and photosynthesis and many of the processes that you have learned in the past. So these interaction between all these different spheres has led to the diversity and wonder that we find on this planet. Okay, this also provides what we call feedback loops. All of you that have taken living environment should be remembering these things: negative feedback loops, positive feedback loops. Okay, and so here we see the interaction. Here you have the atmosphere touching the hydrosphere, touching the geosphere. As the oceans crash against the rock, what are they going to do? They're going to break away little pieces of the rocks that are there from the geosphere, carry them off. Those little pieces are going to be further worn down. Okay, and their minerals may be spread into the hydrosphere. Some of those minerals may be necessary for the development of, let's say, coral. Coral are going to use the calcium and the carbonate to make their shells, to make their bodies, which will build up coral reefs, which will allow for all sorts of life to exist. And so you can see all these things are interacting. You'll have the photosensitive organisms that are existing at the top of the ocean, the plankton, creating the food webs eaten by the zooplankton, and et cetera, et cetera. So you can see all the connections between all these things. So one of the questions we have is, where did this field of geology, where did this field of mineralogy begin? Where did it have its start? Now, it was obviously societies across the world had studied, had discovered things in the ground, had used resources from the earth itself to build themselves up. But the development of the modern science of geology, and eventually mineralogy and the various other fields that we focus on in earth science, would have begun in ancient Greece. Okay? Not to say, obviously, once again, we're not dismissing what other societies in China and the subcontinent of India, the Near East, the Far East, the Middle East, African nations had done. But we're going to focus on the Greeks. And we're obviously going to focus on Aristotle, since he is kind of the father of the modern fields of science, the development, the grandfather, the patriarch of a great many ideas. Not all of them were correct. Some of them were proven incorrect, falsified, through the use of the scientific method as the years went on. One of the ideas that he espoused for why the Earth looked the way it does is this idea that catastrophic events shaped the Earth. Events such as volcanoes and earthquakes and all sorts of cataclysmic events would have had a dire effect on what was going on the planet. So here we have Aristotle. Obviously, we've all seen busts of the man. And one of the places that would have kind of proven this was this beautiful island, which today you should recognize as Santorini, one of the most beautiful places to vacation in the Mediterranean. But during Aristotle's time, there had been records of a huge eruption that devastated and completely changed the shape of that island. A massive volcano went off. This volcano has been linked to a great many things, possibly the downfall of the Minoan society on Crete. There are interpretations that its effects may have been contributing factors in various stories and myths that spread throughout the region. Perhaps even some stories or some of the plagues described in the early pages of the Hebrew Bible. I'm not an expert on those, so obviously I won't go into depth. But there have been stories that had developed and had come out. And obviously, being from Greece, an area that even to this day is still rocked with earthquakes and has volcanic events throughout the Mediterranean, he was a firm believer that things had changed the planet's surface through kind of these cataclysmic events. For this slide, we have a small little video. I'll link it down below, describing the events of Santorini as described by the History Channel. Excellent video. Really gives a good detailed explanation of the various ideas that existed, how they developed, the evidence that we have for the eruption, and the possibility of it happening in the future. So I will definitely link that down in the bio below. So if we keep going throughout time, we're going to discuss what we knew about geology and how it developed in the Middle Ages, particularly in the Near East, Middle East, and Asia. Many areas of the Near East began to be mapped out as people started to use magnetic fields in order to orient themselves to magnetic north. This involved the use of various minerals like magnetite, which were discovered to be natural occurring magnets, and the development of lodestones and the use of lodestones in very simple um, compasses to help direct how we were going to move. So, for example, here you have a sample of magnetite. You can see with the paper clip sticking to it. This naturally occurring magnet would have been able to be used by explorers to develop very simple compasses to help them guide themselves along the coastlines of various areas of both the Near East and the Far East in Asia. As we keep going and we move into the Middle Ages in Western Europe, we see that most of the focus on earth science was primarily in the fields of mining, extracting minerals from the earth, which were used in construction and military technology. You're talking about how did we dig? What did we dig out? Where could we find veins of iron and copper, gold, silver? Okay, these would be minerals that would be critically important for both economic purposes and obviously military purposes and structural purposes. But as we began to dig into the ground, we started to discover things that we didn't see before. We were now capable of starting to see the progression of time throughout the layers beneath the soil. At the bottom of some of these shafts and things like that, strange bones would have begun to have been discovered. Animals that looked like nothing that walked, swam, or flew in the skies. Evidence for new rocks and new formations and events in the geologic past, earthquakes, volcanoes, where none currently existed. All of that would have started to come to light. Okay? But the primary influence, the primary reason behind digging in the earth was the image that you see before you. We were blacksmithing in huge amounts, huge numbers. There was a large amount of the economy that was based on the extraction and the processing and the development of these minerals for various tools, both military and farming and advancements and all these things, which would have been critically important. Obviously, you have all the equipment that you see in the image behind you, which is from the Museum of Art in New York. Here you have a piece of armor, obviously cast in steel with minerals extracted from the ground. Behind it, you have various halberds and helmets that all obviously would have all been pulled or all had material that was pulled out of the ground and shaped into the needs of the Europeans that would be using them. So as the medieval period turned into the Renaissance and the Enlightenment, geology, like many other aspects of the scientific world, was at a crossroads. It had to take the information and knowledge gained from our past ancestors, the tools developed by its current adherents, the individuals like Galileo and Copernicus and others, and move towards the future. But in order to do that, we had to wrestle with ideas that had been a part of the institution, a part of the teachings of geology. Some of those were good, some of those would pass the test, some of those would fall by the wayside. Some of them would be morphed and changed. One of the ideas that we were now grappling with was, well, did the Earth always look this way? Was it changed? What changed it? How does it change it? And that idea, or one answer to that question, I should say, was this idea of catastrophism, which had originally been mentioned by Aristotle. Okay? And at the time, post-medieval period, the scientific and religious ideology that the Earth's features were formed by catastrophic events such as those described in the Bible. For example, events such as Noah's flood and things like that. The idea of an ancient Earth, although not completely new, was held by a small few individuals and had not yet spread to mainstream acceptance. There were various adherents to this idea, obviously since it had originally been taught by Aristotle and he was viewed as the father of modern thought. And so this idea of catastrophism did develop out of his teachings, but also out of the teachings that one would have heard from the pulpit throughout most of one's life. One was the idea that the Earth was only a few thousand years old. Okay? And the second was that events such as Noah's flood, which is pictured in the image above, would have been the cause of all these things. That a great and monstrous tempests had swept across the earth, and only a few had managed to survive the storm. We obviously had certain issues that arise both nowadays and at the time. Like I had said, they had discovered these creatures that looked like nothing that lived on the earth at the time, but obviously was alive at one point. So here we have one of the funniest cartoons of two T-Rexes going, "Oh, did we miss that boat today? Whoops." I've seen this with unicorns too. It's quite funny. Great scene in the show Good Omens about it. Okay? And when we looked at the ground and when we looked at the features of the earth, well, we saw things like this, where you had canyons that looked like water had just cut through it really quickly. And so it was very easy for them to go, yes, an event like Noah's flood would have been possible, because the rigor had yet to have been instituted in the study of geology yet to understand truly what had formed features like this. Okay? In fact, there were people at the time who believed that those creatures that we had found at the bottom of these mines lived with humans in a world just before the flood. Okay? This idea of catastrophism and creationism, particularly young Earth creationism, were incredibly embedded in society. Now, as science got better, the timeline got pushed further and further back, but that would take a little bit of time. So this idea of catastrophism did not just poof out of the blue. It was not just an idea held by unintellectual people. It was actually held by some of the more educated individuals on the planet. There was study, there was research done into it. One of the individuals who was responsible for this was Archbishop James Ussher, who composed a chronology of creation in 1650. What he basically did, this is the individual in question, is he took the lives of the patriarchs as described in the Bible, and using the time frames that were given there, he basically created a calculation where he was able to count backwards, and he came to the conclusion that, including the patriarchs and the time of Jesus and all that, the earth was approximately about 6,000 years old, give or take. As time went on, different scientists, different scholars came to more specific conclusions. They were actually able to conclude what day it was created on, what time, things like that. Although to us it may sound strange, catastrophism was an idea that was held on to by quite a few for a very, very long time. It was still taught in universities well into the 19th century, and it had issues with various ideas that had developed throughout the years, and it was debated not just by individuals who believed in the Bible, but also by scientists who were both Bible believers and scientists at the same time. One of these individuals was this man by the name of Georges Cuvier, and he was a renowned paleontologist who developed many of the ideas of paleontology. He studied the iguanodon fossils of Western Europe, and he was a strict opponent to the concept of evolution after it had been proposed by various individuals throughout the years. He believed that the Earth was a few million years old, so he did move past Ussher's idea of a 6,000-year-old planet. He believed that the Earth was an older, so we can almost view this as an old Earth creation. But he still believed in the idea and stories of creation. He just thought that the timescales were different than what had been presented. He did believe that extinction was possible. Obviously, he had worked on dinosaurs and things like iguanodons, but he believed that these extinctions were primarily due to catastrophes. We know that he was correct in some aspects of this, and that some of the extinction events that would have happened on our planet were the result of cataclysmic events, but not all extinctions. One of the main challenges to catastrophism came from a man by the name of James Hutton. James Hutton was a Scottish geologist and agriculturalist who lived during the early to mid 18th century. And during this time, he made many observations about the Scottish Highlands and the coastlines and areas like that. And he ultimately came to several conclusions which became the foundations of modern day geology. Okay, he created the idea that we would call uniformitarianism. And this was based on the fact that the Earth was extremely old, millions, perhaps billions of years old. And his idea of uniformitarianism kind of became known by this phrase that the present is the key to the past. Now, what does that mean? It means that the processes that we see happening on Earth today, the weathering of rock, the erosion of that weathered rock through water, through wind, through glaciers, the carrying of that sediment, and the eventual deposition of that sediment in a different location, are processes that have happened for time immemorial. It has happened today, it had happened yesterday, and it happened in the distant past. And so all the features that we see are just this slow, incremental processes stacked on top of time and time and time and time and time and time and time. And so the more time that you give them, the more they can work on the earth and the more they can shape the earth. The reason why the valleys are the way they are is because they were carved by rivers slowly sawing their way through. The reason that we have beaches is because of all the material that was deposited there. And so we see that all these processes that we see today are the ones that we will see in the future and in the present. So as we just stated, the ideas behind uniformitarianism is basically that these geological processes that we barely notice, that just kind of sort of happen slowly and slowly and slowly, are minute in their immediate impact, but immense in their long-term impact. Okay? And those that operated, the weathering, the erosion, all these things, slowly build up the planet and the features that we see around us to this day. So the carving of these features, the different patterns that you see in the sedimentary rocks that are here, all of that is this slow incremental process of erosion and weathering and deposition. Okay? These sandstones and conglomerates and gray rock stones that you see here along this coastline, okay, were all laid down slowly over time. The fact that some of them are tilted is because these huge titanic forces within the earth have slowly bent and twisted and tilted the planet's surface. Old rock was laid down, new material was laid on top of it. All these ideas were the ones that were proposed via Hutton. As great as Hutton's ideas were, he needed supporters, he needed followers, he needed individuals that would carry his ideas well past his death. One of these was an individual by the name of Charles Lyell. Charles Lyell was the man who originally published Hutton's ideas, and he actively fought against individuals like Georges Cuvier. And he believed that the Earth was more than 330 million years old, dramatically different than the beliefs of individuals such as Cuvier and other creationists at the time. He was a strong proponent of the concept of evolution and believed that organisms and the planet both change over time. Okay? And just like with any good argument, with any good idea, you need those people who are not only going to agree with you, but also provide evidence and help develop your case. Ultimately, it is the ideas of uniformitarianism that become the pillars of modern day geology, thanks to the hard work and dedication of various scientists creating experiments, theories, hypotheses which are tested, conclusions are drawn, peer-reviewed. Ultimately, we discover that the ideas of uniformitarianism are true. Combine this with the discoveries made through chemistry of things like radioactive decay, and we get this idea that the Earth is much, much, much older than we had previously thought. In fact, we developed the idea that becomes known as geologic time. And geologic time is this idea that the Earth is infinitely more ancient than we had ever believed. In fact, there was a time way before the patriarchs, way before our ancestors, a time before anything that even resembled humans walked the Earth. Older than that, older than the woolly mammoths and the dinosaurs and the trilobites and the original creatures, older than eukaryotic life, older than prokaryotic life. In fact, a time before life, a time before life was even an idea. We stretch our time back to roughly about 4.5 billion years, a number that has been refined over and over again and gets more and more accurate the more we study it. This becomes known as deep time. Deep time is this time that we look at on the Earth, and it's just ancient. And so in order to make a little bit more sense of it, we subdivide it and break it up into various blocks of time. The largest subdivision is this topic known as the eon, or the subdivision known as the eon. So we have the Precambrian, which begins with the formation of the Earth and extends to about 500 million years ago. It then turns into the Phanerozoic, which it literally means visible life, which is the time period when we are capable of seeing actual creatures. Eons are further broken down into what we call eras. You can see it on the screen. We have the Hadean, which is a period of time when we don't have a lot of evidence and a lot of data. It literally comes from the ancient Greek work for Hades, and almost more of a Tartarus kind of concept where you're talking about a time when the Earth was just a fireball and just forming. We have the Archean, which is a period of time when certain land masses would start forming, start to get the beginning of certain events occurring on the surface of the Earth. We have the Proterozoic, which is kind of defined by the first appearance of life, roughly about 2.5 billion years ago. Very simple celled life growing and subdividing and evolving and turning into itself. You then have the Paleozoic, which would be the time of ancient life, the Mesozoic, which would be the middle time or the age of reptiles, or more commonly known as the age of dinosaurs, and the Cretaceous or Cenozoic or era of recent life, which is when you have the age of mammals. All these can also be divided into periods. You see those on the right. You should know some of them, things like the Cambrian, the Jurassic, the Triassic, the Cretaceous. We're currently existing what we call the Quaternary. For recent times, and even some of the older ones, we can further break them down into what we call epochs, when you have things like the Holocene and the Pleistocene and the Miocene. And these would be the divisions that we have. And we obviously can do it the more recent those things are, because we obviously have more specific data. It hasn't had enough time to get eroded away and taken away. So here we have, once again, a geologic history of the state of New York. You have the eons here, the era, the periods, and the epoch if you're looking from left to right. We also have a detail of the certain major forms of life that would be in existence at that particular time. We have some of the family trees here. We have some geologic events that would be occurring in New York. And all the way on the right-hand side, you have the position of the North American continent as the years would have passed on.